Welcome to my presentation on lateral torsional buckling of an I-shaped hoisting spreader beam. My name is Bert Snijder. I am Professor of Steel Structures at Eindhoven University of Technology in the Netherlands. The paper is co-authored by Dirk Ploegmakers, Rianne Dekker and Johan Maljaars. The content of the presentation is as follows. I will give an introduction to the topic, then say something on a test we performed on a hoisting spreader beam, which gave input for a finite element model, with which we did a parameter study, to say something on elastic critical moments and on the applicable buckling curve to be used for hoisting spreader beams. I will finish with conclusions. First, the introduction. In construction, materials need to be hoisted in place, and hoisting spreader beams are used for that. And these hoisting spreader beams can be I or H-shaped steel beams. These are then prone to lateral torsional buckling. They will have a substantial bending moment plus a small normal force. Here you see a typical configuration where S is the suspension point and A and E are the points of load application and B and D are the points where the cables are attached to the hoisting beam. The eccentricity is small e. The length between the points of load application is LAE and LBD is the length between the points where the cables are attached. A hoisting spreader beam is freely suspended and does not have fork end conditions or lateral supports. Should they have had that, then we would have had design rules to cope with it. But they don't have end fork conditions nor lateral supports. For lateral torsional buckling, I use the equations as given in the Eurocode, namely the general case, which are the equations you see here. And this gives you a KLT value with which you can calculate the lateral torsional buckling resistance MB. In this equation goes the relative slenderness for which we need the elastic critical moment. And there are various equations around, and I use the ones given in the Dutch National Annex, which have this shape, as you can see here, where C1 is a coefficient for the shape of the bending moment diagram, and C2 is a coefficient for the height of the load application point. Alright, the aim of this research is to evaluate the lateral torsional buckling resistance for a freely suspended hoisting spreader beam in line with the Eurocode, and this comes down to determining the C1 and C2 values for the elastic critical moment and to determining the applicable buckling curve. First, we did a test because we wanted to see with our own eyes what the behavior of such a spreader beam was. This is the configuration, here are the dimensions, and you can see this is a small scale test from the dimensions. It was also a small scale test on aluminium. The alloy is 6060 T6 and the measured Young's modulus is given here. We also measured other properties, but the test was performed in the elastic domain, so these are not relevant. Connections were applied with minimum friction. For instance, the suspension point you can see here, very practical solution. Also here at point B and D, you see how we connected the cable. And at the ends, you can see we had a simple bucket connected in which we placed weights in order to load the beam. We had lateral wire supports. And if you look carefully, you can see here such a lateral wire and here to keep this point into place in lateral direction. And we had four different support conditions. All points A, B, D, E supported, or only B and D, or only A and E, or no lateral support at all. And that, of course, is the situation which we face in practice with a freely suspended hoisting spreader beam. We measured the displacement delta, which is the relative displacement of point C to the points B and D. We could do this during the test by applying markers and taking photos. And this delta then goes on the horizontal axis in the load displacement graph, on the vertical axis the force, on the horizontal axis the displacement delta. And the lines of the 4 different tests are pretty close, as you can see. So they almost give the same results regardless the support conditions by the wires. Another observation which is important is that the points A, B, D, and S, they remain in one vertical plane, which you can see in this graph, which was taken from the front of the test. So all these points were in one vertical plane. And this is important because it means that we now can apply in a finite element method some boundary conditions. Which brings me to the finite element method. We validated the model against the test, but only in the elastic domain because the beam was quite slender. We used abacus, the measured Young's modulus, the Poisson ratio of aluminium. We used symmetry, as you can see in this graph. And the lateral restraints were placed at A, B, and S. We have seen before that whether or not to use them is not really important, but in a finite element method you have to have lateral restraints. The cables are modeled by link elements, the hoisting spreader beam itself by shell elements, and we use quite a lot of these shell elements. We did a LBA, the result of the LBA is this line here, and we did a GMNIA without any residual stresses and only a small, very small geometrical imperfection, and this because of the fact that the aluminium extrusion is quite straight and has no residual stresses. And then we find a GMNIA result which is pretty close to the experimental results. So we consider the model validated in the elastic domain. Then we modified for steel with the usual steel properties using the true stress, true strain diagram, the von Mises yield criterion, ECCS residual stresses, but now a linear buckling analysis to determine the imperfection shape, and the size was taken as L over 1000, which is the usual size. We neglected, by the way, the root radius, and therefore we denote our profiles with an asterisk. We did an LBA to get M critical and a GMNIA to get the lateral torsional buckling resistance. Parameter study was done. Important parameter is the cable opening angle. The maximum allowed value is 120 degrees for safety reasons. And the sub-study showed that even in that case, the normal force may be neglected. So we could conservatively take an opening angle of 120 degrees, and that is what we used in all our numerical tests. The geometry was varied between certain boundaries, as you can see them here. The eccentricity was also varied between boundaries, taking into account a different way of attaching the cables. For the bigger sections, you would probably weld on a strip with holes, and for the smaller sections, you will probably weld on rings. And this brings us to the upper and the lower bound for the eccentricity. Sections, IPE, HEA, and HEB, and the different steel grades we took into account. First, we looked at elastic critical moment equations, and as said before, this comes down to evaluating the C1 and C2 coefficients, which can be obtained by comparing the LBA results with the results of the equations earlier shown. But C1 and C2 cannot be solved at the same time. Fortunately, we know that C2 is 0 for a load at the neutral axis, and that is where we placed the load first in the finite element analysis. And then we could determine C1 and then shift the load to the center of the lower flange to get a starting value for C2, as we called it. And if we do this for quite a couple of cases, we could find this equation for the starting value. With this starting value, we can now evaluate new C1 values, and we did that as a function of a geometry parameter we introduced, which is FSB, which you see here, and which is here on the horizontal axis. On the vertical axis, we back calculated from our equations C1, And the different shades of gray, the lines in different shades of gray are for the length ratio, the length between the points where the cables are attached and the points where the loads are attached. We could fit these graphs with equations by the least squares method. These are the equations. And in a similar manner, we could also find equations for C2. Now, having C1 and C2 values, we can evaluate M critical. We wanted to see how precise our evaluation was, and we used a statistical evaluation procedure for that of safe brick tile. M critical with the derived equations is the theoretical result, and M critical according to the LBA can be seen as an experimental result. And if you confront the two, you can see we are pretty close. We included in the statistical evaluation the statistical properties of safe brick tile, as you see them listed here in the table. And then the result was a correction B value, which is the mean to nominal value of M critical, in fact, of 1.02 and a coefficient of variation of 6.21. Then we wanted to find the applicable buckling curve. We calculated 153 different configurations for that. You see some of the parameters listed here and the typical failure mode listed shown here. And these 153 results are plotted here into chi lambda standard buckling curve representation. All the dots are the individual 153 configurations, and you see how they compare to our buckling curves. Of course, we also here wanted to do a statistical evaluation for the lateral torsional buckling resistance using the safe brick tile procedure. MB now is the theoretical result when we use the equations. MB according to the GMNIA can be seen as the experimental result if you confront them to each other for a certain buckling curve D in this case, then this is what you get. We used the statistical properties of the table shown before, and for M critical we used the mean to nominal value B and the earlier derived variation coefficient. Well, when we do that and we look at the results for all configurations together as one set, and we look at buckling curve A, then we need, in fact, a gamma value of 1.33. Of course, if we change the buckling curve, this required gamma value also changes. This is for a reliability index 3.8, reference period 50 years, and a weighting factor of 0.8. With a target partial factor of 1.0, we can use the acceptance limit plot. This shows that buckling D can be used. So only for buckling curve D, we find a result below the acceptance limit, which is here represented by the solid line. We did similar analyses for subsets related to the steel grade, section type, slenderness range. For that, I refer to the paper. Then I come to the conclusions. We did look at lateral torsional buckling design rules for hoisting spreader beams in line with the Eurocode. We did a lab test to find out that the most important points on the spreader beam all remain in one vertical plane. So this gave us the boundary conditions for the finite element method. We validated it against the test in the elastic domain and then extended the model for steel. We derived equations for C1 and C2 using linear buckling analysis and a statistical evaluation, and then we used the GMNIA and statistical evaluation to show that the lateral torsional buckling curve D can be used with a partial factor of 1. Thanks for your attention.